Hi and a good day to Dr. Hadi. We are from Group 6. In this video, we are going to present a demonstration of our assignment 2, which is the design and optimization of a 256-point fast Fourier transform using the HLS. So this is our group member who are me and Yishan, Tae Ya-Qian, Yu En-Ti and Yap Sun-Yu. So in this project, we implemented a 256-point FFT using Vitis HLS, targeting a Kintex ultra scale of FPGA. In the first stage of optimization, we used lookup table to replace the real-time sine and cosine calculation, improving the efficiency. And then we further optimized the design using the HLS directive, like the loop unrolling, pipelining, and also the array partitioning to enhance the throughput and reduce the latency. So this step will help us to build a more hardware efficient and high-performance FFT accelerator.
Okay, so in this part of video, basically, I'll demonstrate and benchmark the FFT performance in Python using the NumPy library. So I'll be comparing a clean sine wave here and a noisy sine wave here. So for the first program, sinewave.py, basically this is a program. I'll read a sine wave 10 MHz.dat file provided from Dr. Hadi, and then I'll perform the FFT on this DAT file using the only first 256 sample. So now I'll run the program. So basically, this one is the time domain signal, which shows a clean sinusoidal waveform and as match the expected behavior. And then next one, this one is the frequency domain in magnitude spectrum. So this one is very important, this waveform, which will be used for benchmarking in Vitis later. So we can notice the frequency, the domain frequency is at 4 MHz. So now we'll go to the noisy sine wave signal. This one, I'll generate a 20 MHz sine wave, and also I'll generate the Gaussian white noise in this program. So in this Gaussian white noise program, so the time domain signal have many noisy signal waveform, but then in the magnitude spectrum, we can observe that there's a dominant frequency at 20 MHz. So this one is very important because this is the 20 MHz sine wave, which means that FFT can still identify the dominant component even in a noisy environment. So this one is also a highlight in our experiment. And then now next one, I'll look at the computation time. So for the noisy signal is 3.5 millisecond, and then for the clean wave is also 3.5 millisecond, which means that should be almost more or less the same as they are using the NumPy library for doing the FFT computation. That's all from me.
Now I will briefly explain the step and workflow that I used for the assignment 2 project using Vitis. First, I opened the Vitis and selected the workspace, which is the DSP, and then I create a new empty HRS components, and then I will select the desired FPGA board and also set the clock period to 10 nanoseconds. After that, we can add the source file or create a new source file. So here is the source file for my design. So first one is the FFT.cpp, which contain the FFT algorithm implementations. Next is the header file for the global definitions, and then a 10 MHz sine wave data file as the input signal. And then this is also a test band file to simulate and test the design. So next, let me run the simulation first. While waiting for the simulations, let me explain the codes. So in the FFT.cpp, the main functions are the bit reverse, which rearrange the input data order for FFT processings. Next is the FFT stage, which perform each stage of the FFT butterfly operations using cosine and sine function for the trigger factors. And then is the FFT streaming, which reads input data from the exit stream interface and then process the FFT and send the result back to the output streams. So in the first run, it can read the 10 MHz sine wave data as the input signal and then initialize the input streams. And then it will call the FFT functions and then measure the execution time using the chrono. After that, it will display the result on the console and writes them to the outputs. So here you can see the simulation is successful, and from that we can see that the outputs and also the execution times. Then I will proceed with the C synthesis to get the estimated latency and timing report. So after the synthesis is done, you can see that the timing report and also the latency used in our design. So at the end, we will run the C2RTL core simulations, and we can obtain the final output files for the real and imaginary FFT results. So these output files will then analyze using the Python to confirm the correctness of the design. So here you can see this is the frequency spectrum display using the Python from the output files. Next, we will move to the Rivado to continue the project. So first I will create a new project in Vivado, and then during the setup I will edit all the Verilog files generated from the whitelist, and then select the SAM target board, and then finish the project creations. So after setting up the project, I opened the Vivado Ticker console and navigated to the directory containing all the Verilog files. So using the cd command, I enter the directory, and then I will source all the provided ticker files to correctly add and configure the design files within the project. Next, I will run the linter under the RTL analysis to check for any syntax errors or design rule violations before proceeding further. So once the lint check was screened, I run the synthesis followed by the implementations to map and optimize the design for the FPGA. So after the first implementations, I went to the report clock networks to set up a clock constraint. I created a 10 nanosecond clock period constraint and added it to the design and apply it. After that, I will rerun both synthesis and implementations to make sure the design now compiles with the updated timing constraints. After that, we can view the post-implementation reports, which is the timing report, to verify the setup and hold times meet the 10 nanosecond requirements. After that, we also can view the resource utilization report, and which can view in either graph or table. So from this, we can know how the design use the FPGA resources. And then also have the power report, which includes a summary and a detailed on-chip power analysis. That's all for me for the project flow.
Now I will demonstrate optimization 1, which is the lookup table method used in our project. The FFT.hash file defines the constant, data type, and top-level function interface used in the FFT design. The LUT is defined in the LUT.hash file containing 1, 2, 8 cosine and sine value each, corresponding to the FFT treated vector instead of using function like cos or sine in the FFT set. The program accesses the value directly from the table using an index. This method reduces the hardware complexity and speeds up the calculation during synthesis. While the testband reads a 10 MHz sine wave from the sine-wave.txt file, pass it into the FFT function and collect the output. It also prints FFT result and write them to output file for analysis. Okay, so for the .cpp file, the function FFT state will read from cos loop and sine loop. These values are then used in the butterfly computation for each FFT states. After add this file, we can run the C simulation, C synthesis, and RTL simulations. Okay, these 3 simulations are running successfully, and we can see the synthesis report that has shows an estimate clock period 7.1 at 6 nanosecond. And since the latency is 25 at clock cycle, execution time is approximate 0.001 at 54 millisecond. After implementing the design in Vivado and as shown in timing report, the select is 5.013 nanosecond, indicating that the design made the timing requirement with a comfortable safety margin. In terms of resource usage optimization, 1 shows significant reductions compared to the baseline. LT reduced from 13159 to 1412, Bradford reduced from 6006 to 1553, DSP reduced from 18 to 70. This confirmed that the lookup table method reduced hardware complexity and FPGA resource efficiency. While from the power analysis, the timing part will drop from 0.282 to 0.045 watts, and the total power is measured at 0.512 watt. Okay, that's all for the optimization 1.
Next, I will explain the improvement made in the FFT optimization tool. In the .cpp file, we further optimize the code from the optimization 1 by applying additional HLS directive to enhance the performance and hardware efficiency. One major improvement is the use of the pragma HLS array partition, cyclic factor equals to 4, which was applied to the XR and XI arrays. This pragma partition the arrays into 4 cyclic banks, allowing the parallel access to multiple data elements and improving the memory bandwidth during the FFT stage. Next, we also add the pragma HLS unroll to unroll the inner loop and increase the parallelism in butterfly computation. And also the pragma HLS pipeline to ensure the operation in the loop can start every clock cycle with an initiation interval of 1. In the test bench, the input is read from the file containing a 10 MHz sine wave, and the top-level function FFT streaming is called. And the output results are written to the two files FFT out real optimization tool.dat and FFT out image optimization tool.dat. Next, after verifying the functionality through the C simulation, we proceed to C synthesis, where the timing report shows an estimation clock period of 6.813 nanosecond and a latency of 258 clock cycle. From this, we can calculate the estimate execution time of around 1.758 microsecond. Following that, we run the core simulation to confirm that the synthesis RTR behave the same as the original C model, ensuring that the functionality is preserved through the synthesis process. And finally, the optimized design was implemented into the Vivado for the FPGA deployment. According to the post-implementation timing report, the setup gross negative slack WNS was 5.051 nanosecond and the whole slack was 0.025 nanosecond, indicating that the design met the requirement timing constraint and the resources utilization was low. And lastly, based on the power report summary, FFT optimization to consume a total on-chip power of 0.53 watt with a dynamic power component of 0.063 watt.
Now I will present the result from Vidix and Vivado. This table shows detailed FPGA performance parameters such as clock frequency, clock period, throughput, and slack. The most important point here is that optimization 2 has the shorter clock period at 6.13 nanosecond and highest throughput at around 1.6 pixels per second. Additionally, the slack increased from 0.339 nanosecond in the baseline to over 5 nanosecond in the optimized versions, indicating better timing performance. Overall, optimization 2 provides the best speed and efficiency at the hardware level. From this table, we can see that optimization 1 used the least hardware resource, especially the DSP block and the flip-flop, because it requires sine and cosine calculation with lookup table. The IoT usage dropped significantly from over 13000 in the baseline to just 1412 in optimization 1. Optimization 2 used slightly more resource than optimization 1 due to added parallelism, but still much less than the baseline. This showed that optimization 1 is best for saving hardware, while optimization 2 is better suited for speed. Lastly, the baseline design consumed the most power at 0.282 watts, while optimization 1 significantly reduced it to 0.045 watt. Optimization 2 used slightly more at 0.063 watts, but still maintained a good balance between performance and power efficiency. In short, the optimizations improved the FT design by reducing power and hardware usage in optimization 1, while optimization 2 achieved the faster performance with efficient resource and timing improvement. That's all from us. Thank you for watching.